Hey guys, how you doing? I'm going to run through these two homework problems with you real quick so that you can have them so that we can get started right away on the quiz on Monday. So the first homework problem said to calculate the probability of randomly selecting a point in the blue shaded region. Now, first off, some things that's not really here that we will kind of assume. Number one, that this is a square. Both of these are by themselves half circles. The centers of both will be here and here, right in the middle of each side. And the last thing that we may assume is that randomly selecting a point will land within the square. Okay? So we're not saying, oh, we can select a point that ends up somewhere outside of here. We're not going to say that. So in this problem, there is no number, but we've done a few problems already together in class to know that you may make up your own number if you so desire to. Now, that only covers one specific scenario. So if you want to challenge yourself, you should really try doing this with a variable, which is what I'm going to do. Okay? Now, if you did it with a number, that's fine. Just know technically that is called an informal argument, that you are making your case informally with one scenario, not all scenarios, which would be done using a variable and therefore would be called a formal argument. So if I need to make up a number, and I said again I would do a variable, I'm going to call the length of each side 2x. And you might ask, well, why call it 2x? Well, over here, if this length is 2x, and I'm going to need to calculate the area of this half circle here, I'm going to need to know the radius, which means I'm going to have to cut this 2x in half so that this is x and this is x. That way I don't end up with any fractional pieces, and I want to try to avoid using the fractions as much as possible. So if I want to find a probability of being in the shaded region, I need to find the area of the shaded region and divide it by the area of the whole thing. Okay, so now I'm going to further define what these really meant. The shaded area, well, that's not really a specific shape that we know of. But to get this specific area here, we'd really need to find the area of the square, which is really the whole thing. Oh, crazy E. Where's my back button? There we go. And subtract away the area of the two half circles. Two halves make a whole. And the whole thing, again, is the square. So this has given us now a much cleaner blueprint for what we're going to have to calculate. So the area of the whole square. Okay, well that's 2x by 2x. So 2x times 2x. Then we need to subtract away two half circles, which I mentioned earlier is really just one big continuous circle. So the area of a circle is pi r squared, where our radius is x. So pi times x squared. All divided by the area of the square, which again is whatever 2x times 2x is. So let's simplify this up now. So 2x times 2x is going to make 4x squared minus pi x squared. I can't really do anything with that. All divided by, again, 4x squared. Now, looking at this, there are technically three terms at play. There's this term, there's this term, and there is this term. And what do all three of these things have in common that I could factor out? Well, all of them have an x squared. There we go. There's the squared again. So now what I could do is factor out an x squared on top, and I'd have 4 minus pi left over. And I could factor out an x squared on bottom, and that's really not factoring out, but you get the idea. Now, I've got x squared and x squared here. I may cancel these out. And you might go, well, Mr. G, hold on. You said we couldn't cancel stuff out like that if there was junk in the trunk. And there's obviously a minus sign right there. That's some junk in the trunk. Well, those are technically two different trunks. So this kind of represents one trunk, this the other. So I couldn't cancel out those 4s because they are in the same trunk and there is a minus sign going on there. So I may cancel out those x squareds, which is nice because now I have nothing but really numerical values here. So now if I take my calculator, and let me grab one here real quick, and in my calculator put in parentheses 4 minus pi divided by 4. This is giving me approximately 0.2146 or 21.46%. So that is my probability of landing in the one of the two blue shaded regions. Okay. Now, if you used any other number, like even if you wanted to call the side length 2, and the radius is 1 in this case, you're going to get that same exact answer. Okay. You're just not going to have variables that will cancel out in the very end. So my method applies for any value of x. Meanwhile, if you just chose 2, you're picking a specific value. You're not picking every value. It would take you forever. And you would never finish if you were to pick any possible value for the side length of the square. So that is our first problem. The second problem says calculate the probability of randomly selecting a point inside the circle but outside the hexagon. Okay, again, this yellow shaded region here is where we want to end up. Okay, now one thing is we are to assume that the vertices touch exactly one point of the circle. And you can tell by this hexagon that it is regular. All 6 angles are congruent. All 6 sides are congruent. All right, so let's make this formal. If we want to find the probability of technically the shaded region, we again want to find the area of the shaded region and divide it by the area of everything. And let's get a little bit more specific now. The area of the shaded region is really the area of the circle minus that hexagon. We don't want the hexagon. And the whole thing is really just the circle. Yes, there is a hexagon in it, but technically the area of the whole thing here is the circle itself. Okay? So the circle includes the hexagon, if you will. So we don't need to include it in addition to the circle. So, on the information we have here, we can see here that the radius of the circle is our 7 meters here. So pi times 7 squared minus, and I'm going to leave that for now, and the whole thing down below is pi times 7 squared. The area of the hexagon, it's been a little while since maybe we've done these types of problems. But if you do remember anything, we had to draw in another radius here to really get a feel. So this is another 7 meters. Now, if we drew in all of the radii, we'd have 6 congruent triangles. And we said it would be fantastic if we knew how big this angle was in between the 7s, because then we would have a side angle side, and we had a formula for the area of a triangle involving a side angle side of it. So this is where we took 360 degrees going all the way around the center and dividing it by 6 equal regions. So each angle is 60 degrees. So here again is our side angle side. And that formula, if you have forgotten, the area of a side angle side triangle was 1/2 side times sine of the angle. So now applying that to our picture here, the area of the hexagon would be 6, really, of these. Because when we find the area of 1, then we needed to multiply it by 6. So I'll go ahead and put the 6 here, because we have 6 triangles to make up that full hexagon. And then 1/2 times side times sine of our 60-degree angle. So yes, the 6 and the 1/2 will make 3, which is fine. Now, this isn't going to look very nice if we try to simplify stuff. Okay? This is the point where you might just want to throw all of this into the calculator and get just a decimal from here. One thing to note, though, you will definitely need to put all of this in parentheses up top before you say divided by, and you will want to make sure to put all of this in parentheses when you divide. So if I were to type this in real quick, parenthesis, pi times 7 squared minus 6 times 0.5 for 1/2 times 7 times sine 60, end parentheses, the sine 60, and in parenthesis, my beginning parenthesis, all divided by parenthesis, pi times 7 squared, end that parenthesis. Now, if you have a graphing calculator, you will want to make sure that it is in degrees, which mine was not, because I got an answer that was 129%, so I knew something was wrong there. And I get that this is approximately, if I do 4 decimal places here, technically 0.1730, which is 17.3%. So I have a 17.3% chance of randomly selecting a point that will land inside the circle, but outside of that hexagon, okay, which is more than I thought it was truly going to be. Just looking at these little slivers, you're not thinking this is going to be much. But in reality, it's not. Each sliver, if we divide this thing by 6 slivers, 6 segments, I should say, it's less than 3% for each one of these, which is kind of what you would think. You don't really think about putting them all together, and now we're talking about nearly 20% of the circle are these segment regions. So that is all. If you have any questions, please ask them at the very, very beginning so that we can take that quiz and you have plenty of time to finish it. Good luck to you, and we'll see you on Monday.